Definition of orthogonal and orthonormal sets. A set like S of vectors in an inner product space V is called orthogonal when every pair of vectors in S are orthogonal to each other, perpendicular, everybody. You have perpendicular vectors. In addition, if they are unit vectors, you say, hey, set S is called orthonormal set. So as long as the vectors are unit vector, the magnitude of each is equal to 1, then you call it an orthonormal set. So the distinction between them. For orthogonal set, you have just the inner product equal to 0. To be orthonormal, the inner product must be 0, and at the same time, the magnitude of each vector is equal to 1. Now, if S is a basis, then it is an orthogonal basis or it is an orthonormal basis, respectively. So again, to be orthogonal, you only need one condition. To be orthonormal, you need two conditions. For example, show that the set is an orthonormal basis for the space. It has 1, 2, 3 vectors. One of them is 1 divided by square root of 2, 1 over square root of 2, and 0. This is your very first vector. The second vector is negative square root of 2 divided by 6, square root of 2 over 6, and 2 square root of 2 divided by 3. The third vector is 2/3, negative 2/3, and a third. So to check to see if it's orthonormal basis for the space, we need to check two conditions. First of all, the inner product of pair of vectors must be 0. And at the same time, you need to check to see if they are unit vectors as well. So let us begin. To check that two vectors are orthogonal, you need to find the dot product between them, because here we are in the space. And the space, the inner product is basically the dot product. So here, if you multiply V1 and V2, you have the multiplication of square root of 2 times negative square root of 2 divided by 6. You can cancel out square root of 2. Square root of 2, you get negative 1 over 6. Then the multiplication of the second components, we can cancel out square root of 2 as well. You get 1 over 6 again. And when you multiply 0 by any number, it is 0. But negative 1 over 6 plus 1 over 6 is also 0. So it just showed that V1 is perpendicular to V2, or they are orthogonal. So this is for the very first pair. For the second pair, V1 and V3, the same process. We multiply 1 over square root of 2 times 2/3 plus 1 over square root of 2, negative 2/3, and 0 times a third, which is basically 0. The next pair, V2 and V3. So now just find the dot product between these two vectors, which is negative square root of 2 over 6 times 2/3, square root of 2 over 6 times negative 2/3, and 2 times square root of 2 divided by 3 times 1/3, which is, again, 0. So these vectors are orthogonal, or they are perpendicular pairwise. So the first condition is met. What about the second condition? Which one of these is a unit vector? Well, we need to check the length. The length of the first vector is the square root of the dot product between its components, which is square root of 1 over square root of 2 times 1 over square root of 2 is just a half, plus a half plus 0, which is 1. So V1 is a unit vector. What about V2? The same process. Here you have square root of V2 dot V2, which is 1 over 18 plus 1 over 18 plus 8 over 9. If you take common denominator between them and then take the square root, it becomes 1. Simple algebra, everybody. And then the magnitude of the third vector, which is the square root of the dot product between V3 and V3, square root of 4 over 9. They're just raising this, each component to the second power, 4/9, plus 4/9, plus 1/9, which is 1 again. So these two conditions are met. So for sure, you can say that, hey, I have 3 vectors that are orthogonal. They are each unit vector. So these 3 vectors form an orthonormal basis for the space. Other than I, J, and K that are basically the standard basis, you define a new basis that satisfies these conditions. So other than a standard basis, we defined orthonormal basis for the space here, R to the third. So you were wondering why we are doing this. When it comes to data science, deep learning, machine learning, we try to change the basis so it gives us better perspective about classifying data into nicer sections. So when you run algorithm and you are finding an orthonormal or orthogonal basis, this is basically what you're doing. You're changing the basis for the vector space. Next example for you, an orthogonal set in the vector space of all continuous functions between 0 and 2 pi. So remember that in the vector space of all continuous functions between 0 and 2 pi in general, a closed interval, we define the inner product this way. The inner product is defined as the definite integral 0 to 2 pi f times g. We want to show that the set S, including 1 sine x, cosine x, sine 2x, cosine 2x, and continue this process. List sine nx, cosine nx, these functions form an orthogonal set. So what are we going to do? We're going to basically show that the multiplication of pair of functions here is equal to 0, but we have a nice inner product, which is this inner product for us. We're not going to just multiply these functions. We are going to apply this function as the inner product function. Let us begin. If you start by finding the inner product between 1 and sine nx, this is the definite integral 0 to 2 pi sine nx dx, which is 0. If you find the inner product between 1 and cosine nx, this is the definite integral 0 to 2 pi cosine nx dx, which is 0. But why is that? For example, if you look at the definite integral 0 to 2 pi sine nx dx, this can be written as, from calculus, -1/n cosine nx 0 to 2 pi. If you plug in 2 pi, then 0, this is basically equal to 0. So on the exam, in the homework, when you're proving that the inner product is equal to 0, you need to apply what you learned in pre-calculus and calculus to simplify these integrals. So far we showed that the multiplication of 1 by any of these functions is equal to 0. So when you're writing sine nx, cosine nx, it includes sine x, sine 2x, sine 3x, and so on. Now, sine mx and cosine nx, this inner product is also 0. Sine mx, sine nx, if m and n are not equal to each other, this is also 0. Why is that? If m is not equal to n, then you can use what you learned in pre-calculus. The definite integral 0 to 2 pi sine mx cosine nx is equal to 1/2 the definite integral of sine m plus nx plus sine m minus nx. Well, we just showed that the integral of sine is related to cosine, and here between 0 and 2 pi, it becomes 0. Now, if you find the inner product between cosine mx and cosine nx, this is definite integral of cosine mx times cosine nx. If m is not equal to n, it is equal to 0 as well. Perfect. You can also take a look at the case that m and n are equal to each other, then the definite integral of sine nx times cosine nx dx is equal to 1 over 2n sine squared nx between 0 to 2 pi, which is again 0. So we are just going back to pre-calculus and what we learned in integral, and we can simplify each one of these. So we just showed that the previous set here with all of these functions form an orthogonal set. It means that all of these functions, the inner product between them is equal to 0.